Good afternoon. The moderator of this plenary panel is Rick Stuhlen, retired Vice President of Sandia National Laboratories and a Propulsion and Energy Executive Steering Committee member. Today's discussion will include panelists from Safran, the U.S. Department of Energy, NASA, and General Motors. Ladies and gentlemen, please welcome Rick Stuhlen.
Before we start, excuse us, we need a group picture.
Oh, okay.
You guys stand up. All right. Welcome back from lunch. And thank you, actually, for coming after lunch. Sometimes this ends up being perhaps the most challenging part of the day with the metabolic low setting in another hour or so, but I think you'll find the information here and the panelists very interesting, and I'm sure you'll be as excited as I am to hear sort of the different perspectives this afternoon. We have with us today four distinguished speakers. The first one is Dr. Sunita Satyapal. She is from the Department of Energy. She's in the office of EERE, which is Energy Efficiency and Renewable Energy, and will be talking to us about some of the hydrogen work that's going on there. Those of you who are not familiar with what the DOE is investing in some of these technologies, I think will be quite interested and probably surprised at what's being taken on there. Second speaker will be Dr. Gary Smith. Gary is from General Motors. He's the executive director and runs the global research and development set of programs. So he's focusing on the terrestrial applications of advanced energy technologies and the integration of those technologies into the automotive platform. And again, there are very interesting similarities when you begin to see what they struggle with in terms of challenges and needs to what one also thinks about from an aerospace and aviation perspective. We have also Dr. Ricky Shine. He's the director of engineering and research at NASA Glenn. Again, very broad set of responsibilities as NASA looks to the future for some of the new development needs, and Ricky's going to cover those for us. And then finally, we have Dr. Pierre Baudard, who's he's the CTO of Hercules, one of the units of Safran, and will talk to us a little bit about the European perspective, some of the drivers that perhaps we're not so aware of in the US, but are clear drivers from the European perspective, and then some of the technologies associated with solid storage of hydrogen and perhaps some other things as well. So we've got a great group here. So without any further ado, let me turn the podium over to Sunita Satyapal. Sunita?
Thank you, Rick. And first of all, I'd like to thank the organizers, especially for this session on energy and sort of an alternative perspective from the mainstream of the conference. So first of all, why are we all here today to talk about energy? As a reminder, we spend almost $1 billion a day on imported oil. And we in the US are less than 5% of the world's population, but we're one of the largest consumers of energy. We were actually the world's largest, but China just surpassed the US, and this is one area where we don't need to be first. And we also emit almost 20% of the world's greenhouse gases. So obviously, as other countries start to develop, we need to have, especially in a resource-constrained world, we need to have other energy solutions, and they need to be global solutions. So we cannot just be rearranging the chairs on the deck of the Titanic, and we really need to have a concerted effort, whether it's aerospace or other transportation, stationary power generation, manufacturing, industrial applications. We need energy as front and center. And there's strong support from the administration. Our president has emphasized that we've got to invest in a serious, sustained, all of the above energy strategy. So regardless of shale gas or renewables, responsible and efficient use of fossil fuels, there's very strong support from the administration on energy. And I think many of you have seen that about a year ago, almost exactly a year ago, the president announced the Climate Action Plan. There are a number of very specific goals, not just our 2050 carbon reduction goals, but for instance, specific goals by 2020 to reduce greenhouse gas emissions. Another goal is cutting petroleum imports in half compared to 2008 levels by 2020. Actually, in 2012, oil imports fell to the lowest level in 20 years. And another big driver, of course, is fuel economy standards. So I think everyone's aware of the 54.5 miles per gallon requirement by 2025. So there are a number of federal drivers here. And we have state drivers as well, such as the zero-emission vehicle mandates. And all of these are very, very challenging. So we need to continue to address the portfolio of technologies. So moving on to the Department of Energy, within the Office of Energy Efficiency and Renewable Energy, we fund approximately $1.9 billion per year in research, development, and demonstration activities. And there are three main areas that we focus on. We have renewable power generation, solar, wind, geothermal, energy efficiency technologies for buildings as well as manufacturing, industrial applications, also covering appliance standards. And then we have the newest office, sustainable transportation. And here there are three main areas, vehicle technologies, fuel cells, and biofuels. So what I'd like to do is cover the specific example of fuel cells in my area. And this is an area that's actually not that well known compared to the other technologies. So I think most people are familiar with fuel cells. You can use a number of different fuels and basically convert the energy content in the fuel directly to electricity. There's no combustion, much more efficient. You don't waste a lot of that fuel as heat. Electrochemical reactions, they're modular and scalable, so they can be small enough to power your cell phone or laptop, cover transportation, and large enough to cover multi-megawatt stationary power generation. And when you use hydrogen, obviously there are no emissions other than water and some electricity and heat. And as my NASA colleagues will tell you, the astronauts can actually drink the water coming from the fuel cells. And in terms of criteria pollutants, not just greenhouse gas emissions, there are benefits. One other interesting statistic is that asthma rates have actually doubled in the last 30 years. So from a criteria pollutants perspective as well, electrification does make sense. And then from a resiliency or stationary power generation as well, hydrogen can be used to enable intermittent renewables for energy storage. One other fact is in 2012 alone, climate and weather-related events cost us more than $100 billion. And so grid resiliency is a key goal. And then there are a number of other applications for fuel cells, ammonia production, petroleum refining. So it's not just fuels for automotive applications. So this is actually a very exciting time for fuel cells. I'd like to give you a quick snapshot. How many of you have heard of the Clean Energy Patent Growth Index? You can Google it. But it tracks the number of patents that are issued in the US in the clean energy sector. And what's very interesting and surprising for a lot of people is that fuel cells are really at the top of the list. So 1,000 patents granted in the US 3 years in a row, essentially, for fuel cells. So this really represents the level of investment and the interest seen by industry in this emerging technology area. It is an exciting time. We've seen consistent market growth, starting to get commercial. 35,000 fuel cells were shipped last year. You can see steady 30% growth year over year. And the market is huge. Again, many different applications, transportation, stationary, portable, well over $100 billion. And then also very exciting has been the recent announcements by car companies such as Toyota, Honda. Hyundai just started leasing their first commercial scale vehicle in California, and California has announced significant funding for hydrogen stations, roughly 50 that will be planned in the next 2 years. So why all this interest in fuel cells and hydrogen? All of a sudden, there's basically been significant amount of progress. These are just a few examples of the progress and innovation. We've had more than 50% cost reduction in the last several years. A big driver was reducing the amount of platinum. We basically need to be at $40 a kilowatt by 2020, ultimately $30 a kilowatt for the fuel cell system to be competitive with gasoline engines. Right now, based on all the progress, still in the laboratory, but projected to high volume, we're at about $55 a kilowatt. So we need to continue to make that progress. And just a few stats on the impact of the federal investment. So over 450 patents. I think several of you as well may have been recipients of some of our awards. And it's not just about patents, but there are about 40 commercial technologies in the market now that were directly traced back to DOE funding, 65 emerging technologies that could be in the market within the next 3 to 5 years. And I thought I'd highlight in the next couple of minutes just one specific example, which again is not that well known, and it's a demonstration of the world's first tri-generation energy station. Everyone knows cogeneration or combined heat and power, but tri-generation is where you can produce heat and power, in this case with a high temperature fuel cell. You can see on the orange coming off the anode, you can also co-produce hydrogen. So you have that extra value add of heat and power for buildings. You can use electricity to charge your EVs and co-produce that hydrogen and use that hydrogen on demand as demand increases for hydrogen. So I think this is an example where, and you can use either natural gas or biogas. In this case, it was a wastewater treatment plant in California where we demonstrated a 300 kilowatt fuel cell and 100 kilograms per day station for hydrogen. So this is an example where instead of stovepiping transportation and the stationary sector, there are actually synergies across both of them. So in summary, in terms of the vision for the future, we still need to continue the sustained investment. We still have challenges in terms of hydrogen, reducing the cost of fuel cells, providing hydrogen, delivering, compressing, storing. Again, lots of progress, but still challenges to address. And so finally, in terms of the vision of the future, the key message is a portfolio of clean energy technologies for diverse applications. So whether it's on the road, when we talk about EVs, PHEVs, fuel cells for various applications, we've seen early markets, forklifts, and backup power for cell phone towers. We now have Sprint, AT&T, major companies like FedEx, even Coca-Cola and Wegmans that are using fuel cell forklifts, creating the demand for hydrogen. And so whether it's on the road, even for ship applications as APUs or ports, seaports, there's a lot of interest on the air or in the air for aircraft APUs. I think we'll hear more about that as well. Biofuels, of course, is a big potential play. Ground support equipment at airports, we'll be doing the world's first demonstration shortly. And then even in the homes, most of those fuel cells that were sold, 35 out of the 35,000 were in Japan, and we're seeing major companies like Panasonic and Toshiba. These are small residential fuel cells providing electricity and hot water in the home, operating on natural gas. So in the home as well, renewable power, electrolyzing water, producing hydrogen, and using a fuel cell to power the home as well as hydrogen to power your cars. So finally, a portfolio of clean energy technologies for diverse applications is our vision of the future. Thank you.
Go ahead, Gary.
Thank you, Sunita. And what I'd like to do is to give you a flavor of what's happening in the automotive industry, because like the aircraft industry or looking at aviation or space, a lot has happened. A lot is happening in our industry as well. And as you see some of the things I show here today, think about how they may interconnect with what you're doing within your industry. First of all, this is the challenge that I've always taken. I was an aviator when I was at college, very proud of what has been happening in aviation. But think about what's happened from the first manned flight. If you go back to Orville Wright back in 1903, he flew about 120 feet, 6.8 miles per hour, and he set the stage for aviation. And think about it, it was only 65 years, 1969, July 21st, when the first man basically set foot on the moon. Absolutely incredible when you think about the innovation and what happened in that time. And quite frankly, hands off or hats off to the NASA people. The last 10 years before that 69 walk in the moon, it was tremendous amount of innovation. So let me talk about what's happened in our industry and maybe talk about that 60-year window as well. Because I think it really started back in 1970, and that's when we had the Clean Air Act. At that time, Congress was basically talking about noxious emissions, hydrocarbon CO, and NOx. And basically at that time, GM had the majority of the sales of vehicles in North America. And Ed Cole was our president. And he got up in Congress in 1970 and said, okay, we'll meet the requirements that we want to set for the Clean Air Act. But we need lead-free fuel, which the government mandated 1 year later. We converted all of our engines to be non-lead tolerant. And then in 1974, we introduced the catalytic converter. Now, what's phenomenal is between now and then, between 74 and today, we've taken 99.5% of the noxious emissions out of vehicles. So this was a tremendous effort, a tremendous result, but it really is only part of where we're going in this 60-year window. So let's talk about what's happening now. We dealt with noxious emissions, and now we're dealing with even bigger problems, and one of those is obviously CO2. If you look at what's shown here, I would say, first of all, if we look at California, California does have ZEV and PHEV requirements that are unique to California, but I believe will, again, spread through other states in the US, that between 2018 and 25 will probably result in about 1 in 7 of the vehicles in 2025 in California either being ZEV or PHEV. And probably more importantly, by 2050, well over 80% of the vehicles in California, if you look at these regs, will be ZEV vehicles. So again, you are going to see a lot more electrification, and California really is driving that. But if you look at the rest of the world, again, very stringent requirements around CO2. And if I summarize them, we actually talked before about the 54.5 miles per gallon for North America. Again, a very stringent goal to achieve, which we will achieve. But we've also got to achieve 58 miles per gallon in 2020 in Europe and 56 miles per gallon in 2020 in China. So again, we're in this time of transformation, and this is one part of that transformation, which is around CO2. To give you an idea of that, if we look at personal transportation back in 2000, the size of this bubble is the amount of energy that's consumed in the vehicle park in that country. So think of 250 million vehicles in the US, and again, the size of that US flag is the consumption. We were the 800-pound gorilla. Basically, if you look, Europe's close to us, but consuming a lot less fuel. Look at China on the right, next to nothing, 1.2 billion people, but probably 60 people per 1,000 had a vehicle at that time in China. Compare that to 800 people per 1,000 in North America and about 550 people per 1,000 in Europe. But what happened between then and now and the future? If you actually look at China back in 2005, the industry sold 5 million vehicles compared to 17.5 million in North America. Last year, China sold about 22 million vehicles versus about 16 million in North America. By the end of the decade, we're projecting they will sell about 30 million vehicles. So it'll give you an idea of the size of the opportunity and the size of the challenge in China. And in fact, China, later this decade, will pass the US on the vehicle park, the number of vehicles on the road in their particular country. You also see, of course, India coming on strong here as well. But as we sell vehicles around the world and we look at CO2, we look at our requirements, we got to look beyond the US and Europe. We got to look at all the countries we're selling in, and especially in China and India as we go forward. So this is our portfolio. It hasn't changed in quite a few years. It's about diversification. It's about the current IC engine. How do you improve it? It's about electrification, more and more electrification, getting into ZEVs, and ultimately getting to hydrogen. And make no mistake about it, if you go back to 1974, and if you asked the person that represented me at that time, running the labs at R&D that had just developed a catalytic converter, if you had asked me at that time, well, we're going to take 99.5% of the emissions out of the vehicle, I would have said it was impossible. I would have said the utility of the vehicle would be compromised, and I would have said, sure as heck, you wouldn't be burning fuel. But we are, and we've achieved those goals. And so as we look forward, again, we have very stringent requirements going forward, but make no mistake, the liquid-fueled engine is still going to be a dominant propulsion system for the future. And the reason for that is we're putting a lot of research within the universities, within the OEMs, within the national labs to dramatically improve the efficiency of those engines. And I truly believe that we'll get brake thermal efficiencies in excess of 50%. And that's going to have a significant impact in meeting those future requirements. Necessary but not sufficient. Electrification plays this very important role as well. Sunita talked about fuel cells. I'll not elaborate more on that unless you have questions. But electrification will play a very important role. We have a lot of technologies out there already. And I can talk about those from mild hybrids to the EREVs, to the fuel cells, to the BEV, which you have on the left-hand side. One thing I would say with the Spark that I show there, it has the capability of rapid charging. So it's another step forward. I can charge this vehicle in 20 minutes with rapid charging. It has that capability. So you're seeing the capabilities evolve. But again, the game changer, if it's in conventional propulsion, I believe it's 50% and beyond brake thermal efficiency. The other game changer is the batteries. Today, the Volt, if we look at the energy density in the battery, it's about 140 watt-hours per kilogram. We need to keep pushing the technology, and I believe if we can get up into the mid-300s, 350, 400 watt-hours per kilogram, it will change the game for personal transportation as well. But what about other things that actually impact energy, not in a direct way, but an indirect way? Another mega trend is active safety. You're seeing a lot more alerts on your vehicles. For some of you, you'll see more driver intervention where the vehicle will intervene. Look at the left-hand side there for the Cadillac Driver Assist package. And you'll see all of the features that you have on that Cadillac. That Cadillac today in production has 6 radars, 10 ultrasonic sensors, and 2 cameras with tremendous amount of data fusion to do all of those features. We're also working on that later this decade, we're going to add additional features that are going to give us limited autonomous driving on the highway. And again, we're marching up this curve towards full autonomous operation. A lot's happening in vehicle-to-vehicle communications, vehicle-to-infrastructure, and also getting 4G into our vehicles and making our vehicles as hotspots. So a lot of activity, and what does it all mean? It's about driving towards vehicles that don't crash. While autonomous and driverless vehicles sounds great, the real value to us will be if we can eliminate crashes. 32,000 to 34,000 people die every year because of crashes. Think if we could eliminate that. Think of the impact that has on humanity, and then think about the impact of congestion and other things that will impact energy. The other area is urban mobility. People are moving into cities, especially in developing nations. By 2030, 2/3 of the world's population will be in urban environments, and 80% of the wealth will be in urban environments. We're seeing more and more megacities, more and more hypercities. How do we move people? How do we move people that first mile and that last mile? as they live in these 10 million people cities and 20 million people cities. And a tremendous amount of effort is going on this. And by the way, within these cities, about 40% of the fuel is consumed in looking for car parks. It's looking for parking. So think about V2X capability and what we can do there as well. Not going to touch on all the things we're doing with urban mobility. It's a tremendous area. We're putting a lot of effort on. This happens to show two personal urban vehicles that we've developed, the Envy and the Envy2. It happens to be in the China market, working with an eco-city in China to demonstrate the full capability. But this is just an example of some of the work that's ongoing in this area. So I'll finish by saying, you know, if you think about that 60-year cycle, we're 40, 45 years into it. I believe the next 10 to 15 years will truly transform transportation or personal transportation. Look at what's happening from an efficiency perspective, from an electrification perspective, from a connectivity perspective, and ultimately getting to autonomous vehicles. So we're right in that 60-year cycle. We're right in that last 10, 15-year window. It's an exciting time, but it's also a very challenging time to be in this industry. So thank you.
Good afternoon. So I realize these charts are very busy. I'm not going to hit every point on these charts. Just wanted to sort of whet your appetite for from an aerospace perspective, the things that are really important for where we're trying to go with technology within NASA for aeronautics and also for space applications. So if you look at this chart, we need to make advances in power management and distribution systems. Those systems are starting to become a lot more intelligent. We need to put the smarts in the system where the systems can manage the power load across the systems, be able to get the power to the right places when we need to get it to the right places, be able to handle any kind of surges or spikes in the system. And when we look at developing these kinds of technologies, not only for space applications, because we need to make sure that the systems are robust from a safety perspective and also have redundancy, these technologies also have application to ground-based and terrestrial systems. Not only ground-based and terrestrial systems here, but ground-based and terrestrial systems on other planets. Looking at power and intelligent power controls, we need that from aircraft and also from a spacecraft perspective. We're starting to look at, from an aircraft perspective, more hybrid electric aircraft. And so you want the power system on an aircraft to be as efficient as possible so you can try to reduce weight and try to make the aircraft more efficient. The same thing with the spacecraft. If you can reduce weight, save space, have the system do a lot of things autonomously on its own, you can make that mission a lot more effective. Next chart, and Sunita hit this one, so I'm not going to spend a lot of time on this, but still there's work that needs to be done in regenerative fuel cell systems. And Gary hit this one as well, and Sunita as well, on batteries. Again, the game changer for any type of storage media that you're going to use for a power system is going to be energy density. The types of things that we're looking at to be able to enable deep space missions, outer planet missions, is by increasing the energy density by order of magnitude. In order to be able to do that, you're going to need advanced materials to do that, materials that are significantly different than the suite of materials that we're currently looking at in order to be able to make that a game changer. If we can do that, again, we can be able to carry more payloads out to outer planet type missions. We can be able to get more supplies and more other things up to support our astronaut corps if we're doing a planetary terrestrial mission, say to Mars or to some other planet. Flywheels. There's a lot of work that people have been doing in flywheels, and now flywheels are starting to become more in vogue, especially for terrestrial systems. Just here in Cleveland, Ohio, I was having a discussion with some people at Cleveland Clinic, which is one of our major hospital systems here in Cleveland, and one of the best in the nation. And they've actually gone to using flywheel backup systems for their emergency rooms and also for other critical care type applications. And so nuclear power generation. So in order for us to be able to pursue some of our deep space missions, we're going to need to embrace using nuclear power, being able to do it safely, be able to do it efficiently, and be able to use that because nuclear power has the ability to provide us energy for some of our longer duration missions, especially some of our deep space type missions. And so when we look at that, we're looking at that from the perspective of it being able to power a propulsion system, but also being a energy storage system for that spacecraft, and also an energy production system for a terrestrial application. So if you're on the surface of a planet, be able to use that so you don't have to carry up the large tankage that you would be required in order to complete those types of missions. And so again, we've used those before. There's going to be more work that we're already doing and will be doing to try to enable the use of nuclear power for planetary science type missions, for robotic, nuclear electric propulsion type missions, and also, again, for some of our work that we've been looking at from our Mars architecture as far as using nuclear power as an enabler for those types of missions. Photovoltaic arrays. There's a lot of work that's been done over the years in increasing the efficiency of photovoltaic arrays, not only for, again, terrestrial use, but also for space use. So one of the things that we're working on right now, and this is a cross-agency type activity, is looking at increasing the efficiency of the photovoltaic cells because we are using photovoltaics in part of our mission architecture for solar electric propulsion. And right now we're looking at that to insert that technology into asteroid retrieval mission, which many of you have heard about, is using that propulsion system, which is very efficient, to go out and be able to capture an asteroid and then be able to do a sample return or bring the whole asteroid back. So there's a lot of work, and again, materials is going to drive that as well. And with that, I will pass it on to Pierre.
Thanks, Rick.
Good afternoon.
Try to buy us some time back.
Well, I will present you the main drivers for the energy consumption evolution mainly in the aerospace domain. So I will focus on this kind of application. Well, as everybody knows, climate change and global warming can be a real threat for the future. So we have, I will speak a little about it, more and more regulations for the carbon emissions. And if you look at the contribution of the space aeronautics activities, you can see that today it's not so big because it is responsible for 2% of the global carbon emission. And if we look at the total mobility emissions, it's roughly 25%. The other part, the other 75% is for personal use, consumption, and also by industry. But since the aeronautics traffic, airplane traffic is foreseen to increase very fast in the future, this emission limitation will be of great concern also for aeronautics. These are the areas and the drivers that lead companies and also research institutes into domains of aeronautics to work hard on this subject. The first is the commitment for the reduction of net carbon emission. So the goal is until 2050 to reduce by two the net emissions. And since we can envision an evolution of the traffic, multiplication by 6, this is really a great challenge. So this is global objective related to the climate evolution. Now, if we focus on some specific applications, the airports are first concerned because they are concerned by a very high density of emissions, ground emissions of NOx and carbon monoxide because of ground vehicles, auxiliary power units for aircraft. And another factor is the noise pollution for the surrounding people. The third item I will mention is related to the business customers. Why this kind of application? Because it is high-value applications, and customers from these aircrafts are particularly interested in comfort and noise. So we will see that working on the auxiliary power units for these applications is quite a promising activity. If we look at airlines, they have to, of course, follow the regulatory compliance, reduce the environmental impact, and also, of course, they have more stringent operating cost needs. We work in Safran Group on the electrical generation on aircrafts for two main reasons. So the first one is the general trend to our reduction of emissions, and the second one is technical, is due to the fact that on an airplane, of course, more and more equipment are electrical. So we have to develop the electricity generation on board the aircraft. In this kind of activity, we are involved in the whole chain for electricity production. That means fuel cell, mainly, it was discussed a lot for general application and for automotive, and it's also of main interest for the aircrafts, because it's today we can consider it's a mature technology and the mass efficiency is quite good. This is the first part. The second part, and perhaps the most important challenge for aeronautics and other domains, is the storage of energy. We are working on hydrogen storage. Main advantage of hydrogen has two advantages. First, it's clean, and it's of importance. And second, it has great energy storage efficiency. The main problem is problem of density, and it's difficult to store. And this leads to mass efficiency. The main problem is mass storage efficiency of hydrogen for the aeronautics applications. I will come back on that point a little later on. This figure is to present how hydrogen storage and fuel cells can be technologies that interest a lot of applications. You can see on the left of a picture a wind farm, and one particularity of this kind of power plants is the intermittence of the energy production. So we need to store the energy. Batteries are limited in the total energy storage availability, and hydrogen is a good option. There's a lot of work for hydrogen storage on ground. You can see after that when we can distribute hydrogen to vehicles, so vehicles equipped with electrical engine that can be either using direct electricity or hydrogen plus fuel cells. and buses, and also, of course, aircrafts. So we are at a point where multiple industries are interested in these kinds of technologies, and there are works on all these areas. The solutions are not, of course, always the same, but the basics are the same. Well, that was my last slide. Thank you.
Thanks, Pierre. Thank you to all the panelists for those presentations. And now we're going to open the floor up for questions from the audience. There are mics in the aisleways. If you're not close to a mic and you just want to holler it out, if you're up in front, I can repeat the question. But we now are open for questions. And let me just start this with something that I think is an observation. I think it's a bit of an interesting observation, and that is the drivers that have led to many of the advances in these technologies have come from the governments of these various countries around the world. And most currently, it's around trying to minimize our impact on the environment, whether or not you believe in climate change or not. There is this overriding theme globally around reducing man's impact or humans' impact on the environment. So the governments are driving it. On the other hand, sometimes government regulations sort of get in the way of things from an industry perspective. And so I'd like to sort of ask Sunita and Gary, Sunita representing the government and Gary representing the private sector, how you feel about where we are with regard to the regulatory space. And let me just turn to Sunita first. Do you think we have enough policy in place to drive the technology development that's happening today, or would you actually want to see more demanding or challenging targets set? It's interesting that Europe is a little bit ahead of us in some regards, right? But just in general, do you think we are where we need to be?
Well, I think that we've definitely seen a lot of progress just in the last couple of years. When you look at the very stringent fuel economy standards, for instance, and even in terms of the greenhouse gas emissions reductions goals, the Climate Action Plan, which just came out in June of 2013, lists some very specific goals. So I think we've been seeing a lot of progress from the US side. But I still think that you need that combination of technology. We still need to reduce cost, improve performance to be competitive with incumbent technologies. I think the policies, regulations, and incentives play a very important role, but to get to that widespread market penetration, it's really driven by the market. So I think you really need that combination and the right timing. So when we look at the state perspective as well, it's not all just on the federal side. I think, and Gary talked about the zero-emission vehicle mandate, and now we have the 8-state MOU where basically they've committed to 3.3 million zero-emission vehicles essentially by 2025. So I think we're seeing a lot of different pieces of the puzzle now, so it's not just policy and regulations and incentives. And I think that the timing is really right, where we're seeing some of those technology advancements and the policies can help start that ball moving.
Gary, how does the private sector view this?
This industry is very highly regulated. But I think if you go back and again think about the noxious emissions, if we hadn't had the regulations, we wouldn't have taken 99.5% of the emissions out of the vehicles. And by the way, the good part of that was the US led the way. Those emissions were adopted in Europe. They're now being adopted in China as well. So I think the whole issue of regulations is clearly I think policies and regs that are put together, working together, make a lot of sense. I think there's been, I would argue for the noxious emissions, it was more of an adversarial role between the government and the private sector. I think that's the wrong approach. I think the one fuel economy standard was where we came together and we said, what do we need to do? And we set a standard for the future, which was the 54.5 mile per gallon. None of the industry exactly knew how to do it at that time, but we said, let's take that target and we're going to march to it. I think that was much better than, for instance, all of the states creating their own CO2 standards and just creating a lot of complexity within the industry. So I think you're seeing more and more collaboration, I think, between the government and the private sector. And if we do that, and if we can set our sights beyond the next reg per se, but really say what is our vision, and then set the regulations to march to it, but be economically viable in getting there, then I think it makes a heck of a lot of sense.
Yeah, it's, you know, the thing that we all want is sort of the acceleration of technology development and insertion, not just the development, but actually the successful insertion into our daily lives. And it's fascinating from just a human perspective to think about all of the challenges that are entailed in moving from today, what we know and are comfortable with today, to something that we don't quite know and maybe we're not comfortable with in 5 and 10 years, but we know long term it's the right way to go. So I really do think there needs to be a push, but there also has to be some great technology out there that the consumer at the end of the day wants. I'm not sure what I would do with 3 radars on my car, but I'm sure you'll tell me. I'll be a lot safer, that's for sure. And so, I mean, it's things like that I think that will help the consumer accept and be actually quite enthusiastic about the next generation of technologies. So with that, let me turn it back to the audience. Questions and comments for these folks? Yes?
Some of our work in space, planetary surface power, involves nuclear energy, advanced nuclear plants, because you can't burn fossil fuels, you can't take enough, but nuclear is continuous. And we have advances over the light water reactor technology, such as the thorium fuel cycle, molten salt reactors, lifter, okay, which operate at atmospheric pressure but capable of high temperatures, using closed cycle gas turbine energy conversion. Some of us wanted to say, let's have a spin-off down to terrestrial applications, but unfortunately, NASA is not, maybe DOE NASA combination would be a great way of fostering this spin-off, okay?
That's a great idea.
Dr. Shine might comment on this. Some of us have been advocating the thorium fuel cycle collaboration, but previous administrator, Mike Griffin, said, no, we at NASA are only involved in space. They are not getting, now, even though during the Carter administration, we had been working on high sulfur coal with combined cycle MHD.
Yeah.
Anyhow, so.
Well, let me just come. I know the DOE is still very much interested in all things nuclear, or many things nuclear. And in fact, putting some emphasis on the small modular reactor technologies that ultimately I think will find a place on a terrestrial application. I'm not sure in interplanetary exploration, but let me ask Dr. Shine to comment a little bit about the NASA perspective on nuclear and sort of where
My comment is no comment on that one. That's a decision that will be made at a grade level a lot higher than mine, so I have no comment on that.
I guess this is thank you for the question, though. I think this is a great question to continually raise. There tends to be this cyclical nature to the government's interest in nuclear technology and the development of advanced nuclear power. But I think it's a really important one to keep on the table.
On nuclear thermal propulsion, we have several papers on that, but not for terrestrial power.
Great.
Baseload power generation.
Thanks for your question. Yes? Could you get to the mic? That would be great.
Some of these technologies use strategic materials like platinum, but some of the largest platinum producer, I believe, is in Russia. They're not necessarily friendly to us. So how do you see this impacting the development of these technologies?
Okay. So the question is around strategic materials and potential vulnerabilities to a country, not only the U.S., but to others, who may want to invest in technologies that use those materials. So anybody want to take that?
I can start. We actually have invested at DOE in what we call the Critical Materials Hub. So there have been a number of really consortia with industry and national laboratory and academic experts. So that's one that specifically addresses some of the key issues with critical materials. Then in terms of platinum, that's definitely an issue, and that's partly why when you look at some of the progress, I mentioned a 5-fold reduction in the amount of platinum used in fuel cells. The goal ultimately is to be on par with catalytic converters, non-PGM, non-platinum group metals. But there's also a lot of interest and funding now going into completely non-platinum group metal catalysts. So it's definitely an area of interest, and we take into consideration the fact that these materials, are not easily accessible.
Gary?
I think this is a huge deal for a lot of companies, and certainly in the automotive industry. When we got into after-treatment systems, again, we were using palladium, platinum, and rhodium. One of the advantages we had, we could actually sort of mix and match between the three, and so depending what would happen with the price of platinum or palladium, and a lot of the palladium comes out of Russia as well, but a lot of times you would see a 4 or 5-fold increase in those prices. So I think as we look at developing new technology, we got to make sure that we're not a slave to a given technology or to a given material that we will get from 1 or 2 sources in the world, because again, it can be friendly countries, it can be unfriendly countries, but again, you really don't want to be dependent on that. So that's one of the things you need to look at as we're developing the new technologies. But quite frankly, it's one of the areas where I think the national labs can and have helped us a lot. I can say probably about 12 years ago, we did a lot of work with Los Alamos, and it was because of palladium at the time and the price of palladium. And we looked at some very novel ideas around non-precious metal catalysts as an example, and we created some very interesting technology because of it. But I think bottom line is, as we look at moving into a new area, whether it's neodymium, whether it's lithium, whether it's whatever, you really have to understand basically where you will get that material from, and you really don't want to be completely dependent on the one material.
Great, thank you.
Maybe, can I just add, I think there are some examples. This is an area where we're seeing a lot of innovation. I think some people think catalysts is an old field, but Argonne National Lab just published just a few months ago in Science this unique nanoframe catalyst with 30 times higher catalyst activity than the conventional platinum on carbon. And innovative ideas like a core with a cheaper metal like nickel, and then a thin monolayer skin of platinum. So I think that this is a good example of where we still haven't solved, there's a lot of space for innovation.
Improvement, yeah, good. Question?
My question concerns the NIMBY debate, the not in my backyard debate that centers around a lot of new technologies such as nuclear and wind. And my question is, what does the Department of Energy try to do to try to address those concerns and try to influence zoning laws, not from just a federal level, but towards a more local and state level? And the flip side of that question is, what does industry do to try to gain more general acceptance of, say, hydrogen technology or more electric vehicles?
Okay.
How do you influence the general public to accept this technology?
So the question is something around, as these technologies get developed, where there are concerns, how does the government help alleviate those concerns, and then also how does industry play into that whole equation as well? Is that right? Mm-hmm. Okay. Sunita, do you want to take a stab at that?
Sure. So that's a great question, and we actually do have a lot of activities in that area. So in my specific area, for instance, in hydrogen and fuel cells, we've conducted outreach and training. We've reached more than 30,000 code officials. One of the big challenges is the over 40,000 local authorities having jurisdiction, so permitting of stations, basically consumer acceptance, social acceptance, education is a really critical part of that. So we work very closely with industry, in fact, various partnerships to help educate. I think another important area is the codes and standards. So we're very actively involved. So what should the permitting distances, for instance, for the stations be? There's R&D that goes, behind that to determine what that should be. I think there's still technology, so part of it's outreach. We're very actively involved, but there still is some technology development. I'll give you one specific example. You cannot sell commercially fuel unless you can accurately dispense it so the consumer knows, how much they're getting for what they pay for. And today there's no commercially available cost-effective meter that can dispense hydrogen to the required accuracy for a commercial sale. So the Coriolis meters used in CNG are just not accurate enough for the pressures and temperatures. So that's an example where we still need that technology development. And we're also working to help enable the certification of components, dispensers, hoses, some of the new technologies where the codes and standards and authorities having jurisdiction are just not familiar with the technology. So it's a very important area. I think many times we overlook it. We focus too much on the R&D and the technology. So thank you for bringing that up.
Yeah, codes and standards is a great way to involve a large stakeholder base. It's been done very effectively in a number of industries. I know microelectronics for sure, but that's a good point, Sunita. That's a way to engage a portion, at least, of the public as technologies get deployed.
What about you, Gary? How do you engage?
Yeah, this is one where if you build it, they will come does not apply to our industry. And you've seen that, you've seen it with hydrogen, for instance. Again, I think some of the companies put a tremendous, effort into developing, the fuel cell capability. Like in GM, I think we started back in 1966 with the Electrovan, but we put tremendous effort over the last 15 years. We've done a lot to get platinum out. I think you know that, and getting it down to the point where we have something that we think is viable. But clearly, you need the infrastructure. And if anything, I think the OEMs were building the capability, and the energy companies were even shutting down some of the stations, et cetera, that we already had. So this is something we have to work together. We got to work basically with the DOE, with the government in general, with the energy companies, and with ourselves, and ultimately, again, looking at what the consumer wants and giving them something that they want. But we need to work together to make sure the infrastructure is there, basically with the mobile technology, with the codes and standards, with the regulations, et cetera. And that is, the earlier we work together, the better. Because again, we've had the failures. We had the failures with biofuel was a good example where today there's over, 9 million vehicles that are flex fuel capable in the US. Less than 2% of the gas stations have the capability, and virtually nobody is filling up with E85. Another example where a lot of effort was put in, but we didn't work together on it. I think now you're seeing that is changing, and I think even with hydrogen that is changing. I think there's a much more coherent effort. You're seeing, we're working in California, we're working in Germany, we're working in Japan to really, again, push the whole infrastructure with the technology. But this is a big deal, and quite frankly, as an industry, we have been used to doing things ourselves. The energy companies do their things themselves, we do ours. I think electrification is a much better example. As we rolled out electrified vehicles, there was much more work done with EPRI and others to make sure, again, that there was the home refueling, which again was, again with electricity in this situation. But I think we need to do that because if we get it wrong, we've lost the opportunity. And I think fuel cells is a good example. We were moving very strongly. There was a lot of hype there, admittedly. And now I think we're taking a much more concerted approach, an integrated approach to make it a reality.
Okay. Well, I think we're at time here, so if you would all please join with me in thanking our panelists. And let me thank you all for joining us, and enjoy the rest of the day.